Zoomed in just a tad. Awesome. All right, let's begin. You guys are here, I'm here, let's do it. Welcome, welcome. So good to see you. Hopefully you have something like this sitting in front of you. We're gonna need them for sure. You only need 2 graphs today. So you might just need the front of 1 page. We're just gonna do 2 graphs. We're gonna take our time. We're gonna go slowly through it today so that we can start flying through it tomorrow. The other thing that I think, a couple things that I think might be really helpful to have nearby, a graphing calculator, because I want to show you around that a little bit when it comes to graphing some trig stuff, some good things to know, also some things to troubleshoot in case you run into some issues, some problems that the calculator can give us as we go through that, and also your unit circle, in case you want to take some trips around the unit circle with us, without having to visualize it in your mind's eye. You can just have it right there in front of you, okay? Because what we're gonna do is we're gonna start section 4.5. You don't necessarily need a separate notebook today. We're not gonna write down anything on there unless you wanna have some duplicate stuff written down. Not a whole lot, honestly, that I think a notebook would do for you today. Tomorrow for sure. Tomorrow for sure, we're gonna write some stuff down. So really just this graph paper, a calculator, and some copy of a completed unit circle. The only thing that the unit circle doesn't help us do when looking at some of these things or give us some decimal approximations, because obviously our scale is pretty set here. And so we'll get into that here in a second. But let's do it. If you pick copies of graph paper from me, you notice that I labeled the pages with page numbers at the bottom right, but I also labeled the graphs along the left-hand edge of those graphs, like 1, 2, and then you flip the page, 3, 4, all the way through 40. That might be a little more than we need, but I wanted to make sure you had plenty. It's probably more than we'll actually do over these next couple of weeks, but hey, you got them. Hey, why not? Why not? So I'm going to do graph number 1. So I'm going to try to keep myself organized that way too, so I know how many we've done. And this way, next year, when I teach this again, maybe I won't make quite so many copies, or I'll make more, so I know how many we've got. Okay. And what we're going to do in section 4.5 is we are going to graph 2 trig functions. Our 2 main ones, our 2 unit circle ones, sine and cosine. And I'm going to start with sine first. I could call it y equals, but I'm going to call it f of theta, because that is our input. You can see our x-axis right here, it's radians, right? And I'm going to stick with radians as often as I can, but I like to kind of out loud talk about the degrees as well, because I understand degrees pretty well too. And so sine of theta. You know, this board is going to do its things to me to drive me crazy. I'm going to keep it together, sort of. Okay, so if you wanted to, if you really wanted to, you could get rid of this y and you could call it f of theta. You don't have to. You could come over here and you could get rid of this x and you could really call it theta. That might just be even better. If we want to be super accurate, that's what we would do. This might be the only time I actually erase, I cross off stuff that's already there. If I was making these graphs myself, I would definitely do that. But these graphs are already labeled along the x-axis in terms of those radian measures. And x is fine. Like, it could be sine of x. I don't have to use theta, but theta is really nice to use because it's only for angles. And that's really nice to know what my inputs are going to be. But look what your outputs are. Sine of thetas. Right? That's what my y values are going to end up being. And here's why I'm choosing sine to start with, because sine is y. And so when we graph this function, and maybe you've done this before, I'm going to really take my time, because if I do it the right way the first time, then I can go a lot faster as we go through this. So put up with the basics of graphing trig functions to start. Having our y values be the y coordinates from the unit circle makes my brain happy as a great way to start. So I'm hoping that clicks well for you. But before we actually start graphing, I wanted to share something with you. I'm going to drop something in the chat here in just a moment once I copy this link. it's a really quick, like 30-second visualization of what we're about to do and where this stuff comes from. So keep yourself muted so we're not listening to the ominous music that they have in the background for graphing this trig function. But open up that video real quick. I'm going to talk over it for a second. It's like 30 seconds, but it kind of helps us connect why these graphs come out the way that they do. And what you're going to see is that, this x-axis is our radian measures, and what we're going to do when we graph trig functions, we're going to just open up angles. And we're going to map the y, our y values that go with those radian measures depend, of course, on the function that we're graphing. And because it's sine, we're graphing the y coordinates at that certain radian measure when we open it up. And so you see like the unit circle kind of like roll along the x-axis, and it really just traces the point, because that's the y value. And it gets to the end, and what's cool is that it actually backs itself up and erases it, which is, and you can only have to watch it once. Once you see it once, you can close that tab. You see it back itself up, and what it's really doing is it's opening up negative angles, and you see it exactly traces the exact same thing, which is why when we end up graphing this, you are going to see copies of that trig wave, of that sine wave, just appear over and over and over and over again, however many cycles of that we decide we want to do. The graphs that I like to do, I like to go from -2 pi to 2 pi. I don't like to just do one trip around the unit circle. I like to take two, a positive one and a negative one, so that we can see some changes. It'll also help us when we get to graphs of tangent, cotangent, secant, and cosecant. It's going to help us big time when we start taking these sine graphs and sliding them around, right? Messing with phase shifts and period and amplitude and vertical shifts, and hopefully some of those words you've heard before. If not, awesome, I get to teach it to you for the first time. I'm really excited. I love this stuff. Trig graphs are fascinating, just mind-blowing to me, and I'm going to show you a lot of cool stuff over the next couple of weeks as to why I think they're so awesome. That one video is just going to get us started. Okay, so that's what happens, and that's what this happened to me like 4 times. Second period, let's see how many times I can remember to wiggle the mouse, and if I remember to actually turn off the sleep option. Okay, cool. Let's graph this thing. There's a couple spots along the way, though, in the unit circle where we don't have perfect rational y values. Right, we've got the radical 2/2s and we've got the radical 3/2s. So it is nice, maybe in the space below, to write down the decimal approximations for, like, radical 2/2 is about 0.707. We'll use that kind of as a guide. And then the radical 3/2, that's about 0.866. And you see me going to 3 decimal places. I'm going to do that as often as I can, because that's what we do in calculus. Anytime we approximate, we're going to go to 3 decimal places. That's what the AP exam will do for you next year, if that's what you end up doing. Okay. Everything else is 1/2, 1, or 0, right? And then, of course, all the negatives that go with that. Now, what I want to try to do with this very, very first one is plot every single y value along the unit circle. This scale, however, goes by pi/4s, right? Pi/4, then pi/2, 3pi/4, then pi, 5pi/4, and so on. So we'll be stuck between some boxes sometimes. We'll either be 2/3 of the way in or 1/3 of the way in, depending on what side of pi/4 we're on. So do your best. Forget the rest. Don't worry about anything else. And when you do these approximations, we'll just not worry so much about being perfect, but whatever approximations you do, stick to them. And you'll see what I mean when we start to get to, like, the reflective properties of these trig waves. Okay, cool, let's do it. So what I'm going to do, I am going to think about a scale for my y-axis first. Here's the problem. The x-axis is ready. The y-axis is not, right? We've got 4 tick marks, both up and down, but we want to think about, like, where is that range for sine? What are we looking at in terms of the range of a function like sine of theta? Well, all I really need to think about is how big the unit circle is, because I'm just looking at sine of theta, not 2 sine of theta or 5 sine of theta or sine of theta plus 7 or anything like that. Just the plain old parent function for this sine wave. I just have to think about the range. How far up and down do the y values go? Well, they go from -1 to 1. And that's it. So to maximize the space that we've got, I think that's a really good place to go. Let's go down here, let's make that -1, and way up here, let's make that +1. Okay? And if 4 boxes is worth 1, then every box is worth 1/4. And so if you'd like to, I'm going to write it up here just this first time. I'm probably never going to write these decimals again. But if you want to put like, okay, 0.25, 0.5, 0.75, just as a guide for you to help you hit those correct spots, cool. And then of course in the negative direction, -0.25, -0.5, -0.75. Again, I always write the leading 0 when I'm dealing with decimals, because it would be really easy for me to miss, like if here I am drawing kind of sloppy on a board, might not see those decimal points if I'm as sloppy as I am kind of writing with a thing for a projector. So I like those leading zeros for sure. Cool. But we have to at least put the 1 at the top, maybe the -1 at the bottom as a guide for us. Okay, I'm gonna switch colors so things just stand out a little bit. You don't necessarily have to, but I do like to have multiple colors nearby, especially tomorrow. When we start messing around with some of these graphs, I will always draw the parent function graph on my first graph when I do like 2 sine of theta or sine of theta minus pi or something like that. So I have a reference to look at, but that'll be tomorrow. Today we're just gonna do the parent function. Cool. So sine of theta, the y values. We're gonna start at 0 radians, and let's go positive first. I'm gonna go from 0 to 2 pi, and then we'll go backwards, and we'll see what that gets us, okay? And all I'm going to do is I'm gonna rely on you having a unit circle in front of you. I'm gonna visualize it, and I'm just gonna pick the y values. And we're just gonna plot some points along the way, and we're gonna plot all of them. And this is gonna be the one and only time we plot every single spot. 0, pi over 6, pi over 4, pi over 3, pi, 2 pi over 3, all the way around, okay? Because there's so much estimating and being stuck between boxes. But I do wanna do it once for the first time so we get a really nice looking graph. The y value at 0 radians is 0. So we have a point at the origin. Sine starts in the middle, and always will, okay? Now, so I put a point there. Now, as I open up some positive angles, I get myself to pi over 6. I don't have a pi over 6. I've got a pi over 4, which is at 45 degrees. Pi over 6 is 30. And so what I'm looking at, 30 degrees compared to 45, I'm 2/3 of the way there, right? 15, 30, 45. So I'm 2/3 of the way there. So when I plot this next point, my point somewhere here is going to be 2/3 of the way into that box. Now, I can't do that perfectly. I'm just going to do the best I can by trying to just be like a little more than halfway, okay? And where that happens, like where am I actually going to put the y value? Well, it's the y value of the coordinate at that spot, and that's 1/2, right? Unit circle in front of you, there it is, y value at pi over 6. So I'm going to go 2/3 of the way into this box, and I'm going to go up to that 1/2 spot, and I'm going to put it. Not going to be perfect, no big deal. Do the best you can. Okay, now I can get to actually pi over 4, right, which is that first actual grid line on this graph. Now pi over 4 has a y value of radical 2 over 2, right? So that 0.707 is about where I want to try to be. Well, I've got a 0.5 and I've got a 0.75. 0.707 is clearly closer to 0.75 than it is to 0.5. So when I go to this first grid line and I figure out where do I want to put this point, I'm going to put it relatively close to that 0.75 grid line, but a little bit below. Now I'm making these circles really big so that you can see them. If I'm you, I'm maybe not drawing my circles quite so big, so I can estimate a little bit better. Cool, nice. Okay, now we go to pi over 3, which is just another 15 degrees away from pi over 4, right? So I'm going from 45 to 60. So I'm only 1/3 of the way in because I'm like in that little slice on the unit circle. So I'm going to go 1/3 of the way into that next box. But the y value there is radical 3 over 2. So that's a 0.866. That's kind of in the middle, right? Between the 0.75 and the 1 really would be 0.875. So it's like a little bit below halfway. But halfway is really good. So I go 1/3 of the way in to this next box. And then between 0.75 and 1, I'm just going to kind of shoot for like halfway. Whoop, right about there. Doesn't have to be perfect. Don't sweat. However, I am too much of a perfectionist. I need to at least go right there. Cool. There we go. Nice. All right, pi over 2, a nice happy spot. Y value is 1. And there's the first quadrant. Right? There are all 5 spots in the first quadrant. If you remember our left-hand trick, right? 0 and 1. Cool. Now we got to make our way back down. And the thing about making our way back down is we're going to hit all of these exact same numbers just on the other side. And the second quadrant is just a reflection of the first quadrant. And so wherever you made your approximate landing spots, you want to do those same approximations on this half between pi over 2 and pi. So for me, like my 0.866 spot lines up right there. So when I get myself to that 2 pi over 3 spot, that 120 degrees, and I see the same y value, I know I didn't plot it perfectly here, but wherever I plotted it and wherever you plotted it, go straight across, and that's kind of the height that you want that next point to be at. Okay. The other thing that you want to try to do is realize that you just went through kind of that bigger wedge, right? From the point right at the top of the unit circle, now you go another 30 degrees. That's 2/3 of the way into the next box. So I'm just going to try to do everything I can to reflect the first 5 points to the next 5, right? To these points, I'm going to kind of reflect them right over that pi over 2 line as best I can, okay? So when I get now to this 3 pi over 4 spot, my 0.707 was right there. Okay, I'm just going to cut straight across and right on that grid line for 3 pi over 4. I want in between pi over 2 and pi. I'm going to go right there. Okay? Okay, so 3 pi over 4 was that one. Now we get to that 150 degree spot. We get to that 5 pi over 6. And that's exactly at 0.5. So I know I'm on this grid line, but like how far into that next box should I be? Well, if I'm reflecting over here, I went a full box and then a third, right? Full box and then a third. So just a third of the way into that next box as best I can. It's not perfect. I'm not going to sweat. And then at pi, finally back down to 0. Yay, top half done. And it really kind of looks parabolic, right? It kind of has that kind of that quadratic upside down parabola looking thing going. But you'll see as we make our way back around, it's going to curve back up as we go. And so I don't connect any of my points until I've plotted all of the points that I'm going to. Now that's 1, 2, 3, 4, 5, 6, 9 points just for the first 2 quadrants. We're never going to do quite that many. I probably in the future won't do the in-between grid line points. I'll just land on every nice x value, every nice theta value that I like. I'll have to kind of guess my way up and down a little bit based on these numbers, but that's okay. Cool. Third quadrant action. Now we just kind of go into the negatives, but the same approximations are going to happen, right? Okay, so now we take a big slice. We got a 30-degree slice to get ourselves to 210 degrees to get us to 7 pi over 6. So that's 2/3 of the way into the next box. We want to go down to that negative 0.5, so like right there. And then 5 pi over 4, that's going to be the negative 0.707. So I do my best to go closer to the negative 0.75 than I am to the negative 0.5. Then 1/3 of the way into the next box, 0.866, and right there-ish. And then 3 pi over 2, negative 1. And then I just do the same thing on the other side. They're just reflected over the y-axis, which means I get to reflect this right over the line at 3 pi over 2. So I'm just going to go straight across, reflect, straight across, reflect, straight across. And that's when this starts to go a whole lot faster. If you don't worry quite so much about measuring out every point, you only really have to worry about half of them. The first quadrant up here and the third quadrant down there, and then you can just hit the exact same spots on the other side, 2/3 of the way, pi over the radical 3/2 in the negative, and the 0.707, then the 0.5, and down. Okay, there it is. There's a really, really, really nice graph for one cycle of sine, right? All those y values. But I'm not going to connect them yet because I want to go into the negative as well. Okay, but you can see the wave starting to appear. And obviously the graph that I showed you in that video, they plotted every single point. 1 degree, 2 degrees, 3 degrees, half a degree. We're just gonna have to do our best to connect this smoothly, carefully, once we get it done. But what we're gonna see and what you saw in that video is that these graphs just repeat. They are cyclical. They are what's called periodic functions, where there is a cycle of the graph that happens, and then it repeats in both directions. So I really could just take this whole thing, if I wanted to, I could copy it over to here. And in the future, we will. But let's actually go backwards. Let's go through the negative so you get the hang of dealing with that. But in the future, feel free to take one cycle and just copy it over. Okay, but let's go backwards. Let's go to 0 radians, and let's go down. Right, let's open up that negative angle into that quadrant and see what happens, okay? So now we're going down in, and so we want to hit all those nice spots. So we're going to go to negative pi over 6, which is really 11 pi over 6, right? Because we're just going down instead of up to get ourselves there. And that is going to be the exact same value as it was right there. So that's that 2/3 of the way to the left and down to 0.5. Oh, second time, got me. Where's the over under on that? I don't know, it's gonna be like 4 or 5. There we go. So like right about there. Okay, negative pi over 4 is really 7 pi over 4, but we're just going down to get there. That happens at 707, so kind of like right there. Negative pi over 3 is really 5 pi over 3 going that way. That's the 0.866, so another 1/3 of the way in here and about halfway between 0.75 and -1. And then negative pi over 2, we're really just at 3 pi over 2, we're down to negative. Okay, and that's all we're doing, is we're just making our way around, and because it's sine, I just care about the y values. Don't care about the x values at all. All right, let's speed this process up. Let's just mirror our way back. Boom, 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 boom. And now we make our way up. And truthfully, you can just take this right here and plop it right there, okay? Or you can say, you know what? Negative 2 pi, that's the beginning. Because negative 2 pi gets me back to the start. And if I'm going from left to right, I am opening up angles in the positive direction. Left to right opens up positives, right to left, we're opening up negative angles. Because I can go to 2 pi and 4 pi and 6 pi and 8 pi, or I can go to negative 2 pi, negative 4 pi, negative 6 pi, negative 8 pi. This thing goes on forever. All right, let's finish this thing up. I'm gonna go left to right, and I'm just, you can see, I don't know if you can see, like, I'm just looking back and forth. I'm just trying to copy that one was gotta be 2/3 of the way in. Boom, boom, boom. And then I just mirror my way down. Use that understanding of this reflective property. So nice. And there it is. Man, does that look good. Such a nice wave. So many points though. So many points. Okay, first time around it was nice to do. Let's connect it though. And we have to do this freehand, but you want to do it smoothly, carefully. Really, really nicely. Arcing your way to that maximum spot at 1 to the minimum spot. Really kind of taking your time. Hitting those points as best you can. Doesn't have to be perfect. I'm using a much bigger marker, just showing up on here than I would probably use in real life. Gives me some flexibility, and there it is. That beautiful, perfect trig wave. Okay. Now, these do go on forever, so it is nice, even though our graph stops, to kind of extend this out on the left a little bit and put a little arrow. Extend this out a little bit and kind of put an arrow. Makes it look a little bit better. And these kind of graphs, these waves that go on forever, the ones that resemble a sine wave, this is like top 5 favorite math word for me of all time, just because it's fun to say. Graphs that look like these are called sinusoids. I don't know, it's just, this is funny to say. Graphs that resemble sine, okay? We got these waves, cool. Now what you're looking at are 2 full cycles, right? We've got 1 trip around the unit circle and then another, so 2 full periods of sine. The period for sine is 2 pi, right? Because that's how long it takes for you to get around the circle. For you to see the full sine wave from here to there, 1 full sine wave. Okay, so we're looking at 2, and I like to do that, especially when we, like I said, when we get to other kinds of graphs, it's really nice to look at that. And there you go, okay? Now, this obviously can be graphed in your graphing calculator, and we want to use that to help us out a lot. And so I want to kind of pause here for a quick second in the graphing by hand. I'm gonna go down here for a second. Oh, is this off to the side? Nobody's home. There we go, center up. And I want to share my screen and show you in the calculator some cool stuff that shows up, and also some stuff that screws us up a little bit. I just have to kind of undo some of the things that I did second period to show you what happens. I know I haven't shared my screen yet, don't worry. I want to get to the right spot. Cool. All right, now I am ready to share with you some calculator stuff. Because man, this gets so much easier if we can use a calculator to help, and I'm a big fan of it. I want us to have the calculator nearby to help us do some of this graphing. So let's do it. Either watch me or take it out and play along with us. Let's graph some sine, okay? So I went to y equals and cleared out everything that was there. And then right here in the middle of your calculator, those are gonna be your trig buttons, okay? So you've got sine, cosine, and tangent. They didn't bother putting cosecant, secant, and cotangent because if you wanted something like cosecant, you could just do 1 over sine. Yay, now it's cosecant. And we'll look at what that looks like probably next week. But we just wanted sine, right? And you can see, though, that it opens up this sign of something, right? It's asking for an input, right? And, of course, that input is going to be the angle. Now, our variable button next to alpha here, the one that we normally press just for x, like if we're doing x squared, you know, polynomials, whatever, also has theta there. But the calculator does its thing. It will always just draw the x instead of the theta. I wish it would do both. And T is for parametric stuff and N for sequences. But x is good. I'm happy with that. Let's just close out what we've got. And now, most of the graphs that we've done in the past, there was a nice starting view to kind of begin with, right? And that was zoom standard. So that's what I'm going to do. I'm going to go zoom standard, and let's see what we get. That does not look like that. Why? What do we need to fix? We typed in sine of x. That's what it's graphing. What do you think might be the issue, the way I'm going to come back down here, that might be the issue with what we've got in terms of the way that this graph is set up? Unmute yourself if you've got ideas as to what we can fix.
You just need to zoom in, right?
We are definitely in a wrong kind of window, but why is the window wrong? Because if I zoom in, so zoom number 2 and press enter to get to the center, I'm still just looking at that, just a smaller section of a line that it just kind of looks almost linear.
The scale of the x-axis is off.
Okay, so my scale is off a little bit. Now, what do you mean by that? Like these tick marks right here?
So the tick marks in the standard are like going by 1,
Right.
but on our graphs that we made, it's going by pi over 4.
Okay, so if we change the x scale, so pi's right here, so second caret, so pi over 4. If I press enter, it's going to give me the decimal approximation for that. That changes where these tick marks are. Very good. So that's a really important thing. If we want this graph to look like that one, or that one to look like this one, we want our scales to be the same. So I'm a big fan of changing the scale to match what we've got. Cool, good start. What else? Why do we still see the same kind of picture?
You need to be in radians.
Oh, there it is. Look, we're in degrees. Look at what our window is, -10 to 10. That's -10 degrees to 10 degrees. We're in this tiny little space like right here. We gotta be in radians if we want this thing to make a whole lot more sense. So that's mode. My mode, and you can see it here, was in degrees. I gotta go to radians, press enter. Now I'm in radians. Now let's graph it. Now we're -10 radians to 10 radians. Now remember, that's not -10 pi, that's just -10. Remember, 1 radian is the angle whose arc length is the same as the radius. So I'm opening a circle, right? And I'm drawing an arc that is the length of 1 because we're in the unit circle. That looks way, way, way better. Now I'm in radians. Now, sure, I'm -10 radians. That's like 3 full trips around, that's okay. From -10 to 10, we're seeing at least, let's see, 1, 2, yeah, almost like 3 full trips around. So we can mess with this window a little bit more to make it look like this, right? -10 to 10 is like negative, that's like here, like -10 to 10. We can change that if we wanted to be -2 pi to 2 pi. And of course, it's going to just go with the decimal approximations for it. Now our graph will only show there's 1 and there's 2 full cycles. Good. Look at our Y scale. Zoom standard, remember, that's where we started. So that's what our window defaults to. Our Y min and Y max, that's still -10 to 10. If we want to see exactly the same picture, we want to do exactly the same thing. And we could even change our Y scale to be that 1/4. And now we see the picture that we want. Okay, now that's really nice that we can adjust our window, our mode, our settings to be whatever we want. If you want to make sure that what you're graphing by hand is exactly what the calculator wants to see from us, then create a vision, create a window, that's what it is, right? Create a view for yourself that's exactly the same. Just make sure that if you're in degrees, you're in degrees. If you're in radians, you're in radians. But if you're in degrees, then go -360 to 360, right? But that took a lot of thinking and changing and messing around with stuff. Man, it would be so much nicer if the calculator was cool and it had this nice preset zoom option for when we're graphing trig. Do you see one?
Z trig number 7.
Yeah, look at that. Now, it's not exactly what we just saw, but man, it's so nice to be able to just click zoom trig anytime we graph trig, and it will do all of that stuff for you. If your mode is degrees, it will adjust your X scale based on degrees. If you're in radians, it'll adjust it based on radians. You don't have to worry about making the switch. I like to hang out radians whenever I can, but degrees are nice if you're doing like inverse trig stuff, like inverse trig of radical 2/2 or whatever. But there it is. Now the window is not exactly the same. It's actually more of a little bit past -2 pi and a little bit past 2 pi. This one obviously go -4 to 4. But you'll see when we get to things like tangent, cotangent, secant, and cosecant, we're going to want a bigger range anyway, because we're looking at different kind of values. We're not just stuck in the unit circle. Now we're doing proportions of unit circle values. So a lot of different stuff happening there. Cool, nice. Zoom trig, my favorite. Use it all the time. Nice. What time are we done? I forget. We started at, I can stop sharing my screen now. If we started at, let's see,
We're done at
10:55. Okay, so we have a couple minutes. Okay, let's do cosine real quick, and we'll get out of here. Love it. Perfect. Good timing. All right, so I'm gonna get rid of this. That was number one. Now let's do cosine. So I'm gonna call this graph number 2. So you can go down to that next one if you have copies of this. Let's change it up. Let's go g of theta equals cosine of, oh my goodness. That says cosine of theta, you know. I like the same scale. Let's go 1 on top, -1 on the bottom. I'm not going to worry about marking off those tick marks in between. And we're also going to make our lives a little bit easier here. And we're going to skip all the pi/6s and pi/3s in between. Okay? And I'm cool with that. Moving forward, I'm good. We don't have to mark off all of those necessarily. The really interesting things with functions outside of sine and cosine happen at pi/4s and pi/2s and stuff like that anyway. I mean, we'll still mess around with that, but let's go for cosine at this point. I'll go with the red dots here. And now what we're doing though, our x values, our theta values are still radians, but the outputs, the y values of the points that we are about to plot are the x coordinates. Okay, so we're going to open up an angle, and where I'm going to plot my point is based on the x value. Right? Sine is y, cosine is x. And so when I start at 0, or we'll go positive first, when I start at 0 and I'm thinking about where should I put that point, I look at the x value of the coordinate at 0 radians. Remember, there's like 3 parts to trig. There's an angle, and there's an x and a y. But when we're graphing in 2 dimensions, I can only pick 2 of them. Right? The input is always going to be my angle. The output is some relationship between x or y, or, you know, like I said, some proportion of that. So when I look at the x value at 0 degrees, 0 radians, the x value is 1. Okay, like I said, sine start at the midline. Okay, I'm gonna even write this down because I think it's so important. Cosine starts at its maximum. Okay, and that's going to be really helpful for us in the future. Okay, sine starts at what's called the midline. We'll get into that more tomorrow. Okay, it's going to start in the middle. Cosine starts at the max. Cool, and then we go. Now I'm going to skip the pi/6s and the pi/3s. We're just going to do multiples of pi/4. So I really just need the 0.707s along the way. So that one's right. Oh, I need my good one. So at pi/4, 0.707. Okay, at pi/2, 0. 3 pi/4, negative 0.707. At pi, negative 1. Okay, now remember the curvature that we have to deal with, okay? This looks almost kind of straight. It's really not. It's really not, which is why we want as many points as we can. Now I make my way back, and it's really just going to mirror itself over. So at 5 pi/4, we're at negative 0.707. Close. 3 pi/2, we're at 0. And positive 0.707, and back up at 2 pi. Okay, and now because we're good at this, I know that sine and cosine and all of our trig functions, you'll see, are all periodic, they're all cyclical. I can take this, copy it to here. I can start at negative 2 pi at its maximum, and then just make my way around 0.707, 0, negative 0.707, negative 1, and up pi. Now, before I connect this, and maybe you already have, but if you haven't, or even if you have, take a look. I'm going to do something to help something stand out to you. Watch the collection of points that I choose to connect first. Now, I'm not going to do this any other time, but right now. What graph does that look like? It looks like sine, because it is. Sine and cosine, even though sine starts at the midline and cosine starts at its maximum, they both are the same wave, just phase shifted one way or the other. And you don't have to do this, but I'm going to really quickly, I'm going to put sine on this same graph just so you can see it. You can see how fast I'm going. This is how fast you will potentially be able to graph it. So red one is sine, red one is cosine. The blue one I'm about to draw is sine. Just for your reference, you don't have to draw this in the same one because yours is right above it. You can just look at them. They're the same graph, just shifted over. The reason being is because both sine and cosine, they both are sinusoids. They both follow that same path, that infinite wave. Let's put an arrow at the end. They both go on forever. Okay, so when I talk about sinusoids, I'm not just talking about sine graphs. We kind of lump them all together. We call them sine waves because whether it's sine or cosine, I can find an equation for any wave using either sine or cosine. Depends on where I want to start. Do I want to start my graph in the middle and go up? Or do I want to start my graph at the top and go down? Totally up to us, depending on what they ask of us to do. Ta-da! 4.5, the beginning of 4.5. We will finish 4.5 tomorrow as we start messing around with these. We're going to make them bigger, stretch them out, squeeze them, shift them around, and play with them, and try to get a sense of what the equations tell us about how these graphs are going to look. Okay, so there we go. Look at that, 20 seconds to spare. The 20 seconds I need to tell you that I also posted anything and everything that you would need to get signed up for See You Succeed for the spring for college trip. Okay, separate announcement that has the link to the registration, a link to the website, all the important dates, the information about the course with the name and the section and tuition and all that stuff. Okay, so I'm good. I'm done. Nothing you need to do for me except come back tomorrow. Have a great day, everybody. Remember, homeroom is where you are headed next.
Bye,
It's
thank
either your 5th or 6th period class. See ya. Bye. Thanks, guys.
Thank you.
You're welcome. See ya.
Thank you.
Bye, Gracie.